Hello, dear friends. In this lecture, I am going to introduce you to a very powerful approach to analyze complex systems, whether they are linear or non-linear. Let's start. So, first of all, here is given a system. So, system is a set of elements with some interrelations between them. Okay, and on the basis of interrelations between the elements, we can divide systems further into two types. In one type where elements interact, and in another type elements have formal interrelations between them. So in the previous one, state variables change with time, so such type of systems are known as dynamic systems. And in the another one where state variables not change with time, so they are known as static systems. Okay, so here what we get is some variables are changing with time. Okay, and in this there are formal relationships between different state variables. So such types of systems can be found in civil structures or when we talk about the morphology. Okay, and here dynamical systems, we can have examples in neuroscience, economics, other physiology, and many more. So moving ahead, now we will talk about the types of dynamical systems. So on the basis of continuity, we can divide dynamical systems into continuous and discrete. So when state variables can be of continuous form, we can use the differential equations to describe the evolution of system with time. And in another case where the state variables are discrete, we use difference equations, or also known as iterated maps. So in this lecture we will continue with the differential equations. So differential equations also can be of two types. One is ordinary differential equation and another one is the partial differential equation. So ordinary differential equations are equations that involves only one independent variable. Here is the example. Here the time is the only one independent variable. Order may be more than 1, 2, 3, but the independent variable is only 1. So such type of systems can be defined using ordinary differential equations. In another case, the partial differential equations, there are more than one independent variable. Okay, like one example is the heat equation, where independent variables are time and space. Okay, so it may be one dimensional, two dimensional, or three dimensional space. So moving ahead, so now comes a very important slide, is the representation of a system. So how we represent a system in case of non-linear dynamical approach. So a general framework of ordinary differential equations to represent a dynamical system is, suppose we have a system characterized by some variables, let's say x1, x2. In this way there may be many variables. So how we will, a general framework is to represent like this. On the left hand side we can use the x1 dot is one variable and it is of some function f1 of another variables, state variables. Okay, similarly x2 dot may be another function f2 of the state variables. So in this way we can represent all the state variables may be a function of another state variables. So this is a general representation of a non-linear dynamical system or any dynamical system, linear or non-linear. So this is very important. Okay, and here we should mention that x dot is equivalent to dx by dt. So moving ahead, so there may be many types of systems like chemical systems, there may be population biology. You can take examples from population biology, some ecosystems, or maybe velocities of planets in the solar system, and lot of other examples. So now we will take one example from a mechanical system like the damped oscillator. So damped oscillator is where one oscillator is there, let's say a spring mass system. Okay, it has got mass m, it is a k is the spring constant, and there is resistance present that cause the damping of this system. So its mathematical equation or model is the forces acting on this block is minus kx as in general due to the spring, and because friction is present we can also write minus bv. Okay, so we can write this as an equation A. Now as we know, F is equals to ma, and acceleration is basically d square x upon dt square. We can also write A like this. So we can write m x square d square x dt square as x. We can put two dots for this. And similarly we know v is equals to x dot. Again that is dx by dt. So first of all we have changed some notations into x dots. So now equation A can be written as, equation A is now m x dot, okay, equals to minus kx minus bx dot. So in this way we have written the equation A. Now what we want to do, we want to represent this equation into the dynamical framework. So for this we have a simple trick. Take x1 is equals to x, okay, and take x2 is equals to x dot. Okay, now this implies x dot is equals to x, means if we differentiate both sides, so that is equals to x dot. And again x dot from we can see here x dot is equals to x2. So x1 dot is equals to x2. So this is our first equation, and the second equation is we will differentiate it, x2 dot is equals to x double dot. Okay, so now we will put these variables in our previous equation. Let's say this is equation B. So again we can put here, let's say m x dot is equals to x2 dot minus k, and x is now x, we can put x1 for x and minus b x dot, and x dot is x2. So x2 dot is equals to minus k upon m x1 minus b upon m x2. So finally we will take this equation first. x1 dot is equals to x2, and another one is x2 dot is equals to minus k upon m x1 minus b upon m x2. So this system of damped oscillator can be represented by using two variables x1 and x2, and this is the dynamical framework in which we have written this equation. Okay, this system is said to be linear because all the powers, all the x1 on the right hand side and x2 on the right hand side have the power 1. It has a power 1, it has 1 power 1, it has power 1. So it is it's a linear system. In case if it is not 1, power is not 1, then we can call it a non-linear system. So this is an example of a linear two-dimensional system. So let's take an example of a non-linear system. So any non-linear system that involves the products, powers, or any other function, so we can call it a nonlinear system. So this is again an example of a nonlinear system. So we can also write the system as, let's take x1 dot is equals to again x2. Similarly, what we did before, we will take x1 is equals to x and x2 is equals to x dot. So from this we can, it implies x1 dot is equals to x dot and that is equals to x2. Okay, and here again we will, if this implies when we differentiate it, x2 dot is equals to x double dot. So just put x2 dot, we will put x2 dot from here. So x1 dot is this and x2 dot is minus g by L sine x. So in this way we have represent this system into a dynamical framework, a set of equations, set of ordinary differential equations in the dynamical framework. So this representation is very important. So let's move ahead and let's know about few terms. One is the phase space. Okay, so this is important thing because a lot of analysis in nonlinear equations can be done using the geometrical methods. So first we will learn about the phase space. So any system we know is characterized by variables. So when we make a system like this and represent, this is the x1 is a, let's say, state variable of the system and x2 is state variable of the system. So in this way, this such sort of graphical representation or space, we can call it a phase space. Okay. Now we have restrictions here. As the number of variables will increase, we can't represent more than 3 variables. But definitely we can analyze more than 3 variables using the algebraic methods and linear algebra. Now another term is the trajectory. These solutions correspond to the moving point along a curve in this space is called the trajectory. So previously we have seen the phase space. Let's say this is the phase space, x1 and x2. If there is some initial condition, let's say our system is at this position, this is the initial condition at 0, this is x2 at 0. Now if this point moves, the system is moving in this way. So these all are the different points in which system is moving. This is called the trajectory. Trajectory is showing the behavior of the system from initial states. Now we will consider one more important thing. What are linear systems? So linear systems is a property where we can break down the linear systems and we can superimpose also. So let's understand this by using an example. So this is a mathematical definition of a linear system. But let's say there is an example, y is equals to, let's say, 2x. So one system is represented using this thing. Okay, now if the property is that if y5 is equals to, let's say, we can write 5 as 2 plus 3. Okay, if this equation or this system follows this property, so we can call it a linear system. Otherwise we will call it a non-linear system. So let's take this example and we will see it. So x5 is basically just putting the value of 5 instead of x, we got 10. And similarly this is equals to this should be equal to y2 plus y3. So y2 is again putting 2 here, so we will get 2 to the 4 and plus we will put 3 in this x, we will get 6. So definitely 10 is equals to 10. So this is a example of a linear system. Let's take another example. Y is equals to x square, and again we do the same. If just we write 5 as 2 plus 3, and if this is equals to y2 plus y3, then we will call it a linear system, otherwise not. So as we know, y5 is, we will put 5 in this x, so 5 5s are 25. Okay, now y2 is, we will put 2, so it is 2 2s are 4, and y3 is, we are putting 3 in x, so 3 3s are 9. So in this case 25 is not equals to 4 plus 9, that is 13. So this is an example of non-linear system. Okay, now a very important slide regarding the overview of the dynamical system. So let's say we have two axes. One is, here is the n, shows the order or dimension of the dynamical system. So here our dimension is 1, here it's 2, it's more than 3, or it is very large, or there is a case where it is in a continuum. And another axis, we have some linear systems and some examples of non-linear systems. So we will first see the linear case, and then we will go to the non-linear case. So here it is. So linear systems. So linear systems, when they have one-dimensional linear systems, so they perform the phenomena of growth, decay, and equilibrium. So these all are the terms related with linear systems of dimension 1. You can see exponential growth. Examples are the RC circuit, resistance capacitance circuit, or radioactive decay. Okay, so such equations show one-dimensional behavior, linear behavior. When n is equals to 2, when a linear system requires two variables to describe it, and it performs oscillations. So such type of oscillations can be, examples are linear oscillators like mass and spring, RLC circuit, two-body problem of Kepler and Newton. So these are the examples of two-dimensional linear systems. When n is greater than 3, like civil engineering structures, or in the some systems in the electrical engineering, they perform such type of, these are the examples where n is very much greater than 3. When n is very large, some collective phenomena like coupled harmonic oscillators, or solid state physics, or molecular dynamics, equilibrium statistical mechanics. So these are examples of systems, dynamical system, where dimension is very greater than 1, very large. Now in the continuum phenomena, examples are the waves and patterns, elasticity, wave equations, electromagnetism, Maxwell, quantum mechanics, heat and diffusion, acoustics. So these are examples of continuum. Now let's move to the non-linear part. Some examples of non-linear part where the dimension of the system is 1, so we use some new terminologies like fixed points and bifurcations. Okay, so examples are the overdamped systems, logistic equation for single species in population biology. So these are examples of one-dimensional nonlinear systems. When there are two-dimensional nonlinear systems, examples are the pendulum and harmonic oscillators. Limit cycles is a phenomena that is performed by two-dimensional nonlinear systems. Similarly, biological oscillators like neurons, heart cells, predator-prey cycles, nonlinear electronics are the examples. When n is equal to or greater than 3, so here comes the chaos, phenomena of chaos, and the behavior can be shown by strange attractors. Three-body problem is an example of it. Chemical kinetics, fractals, forced nonlinear oscillators are few examples of this. When dimension is very large, some coupled nonlinear oscillators, lasers, nonlinear optics, non-equilibrium statistical mechanics, heart cell synchronization, neural networks, immune system, ecosystems, economics are the examples of this one. And examples of continuum are the non-linear waves, plasma, earthquakes, general relativity, quantum field theory, reaction diffusion, biological and chemical waves, fibrillation in heart, epilepsy, turbulent fluids, and ultimately the life. So this is a column where these all are the frontier areas of research. Okay, so this is a beautiful classification of lot of systems into linear and non-linear and based on their dimensions. Hope you enjoyed this overview. Okay, meeting you in the next video. Till then, thank you.